course schedule and the problem, its second part, which is course schedule 2. Now I will explain you both of the problem one by one. Now it says now there are total of num courses. Means this is the number of course you are having. You have to take labeled from 0 to new courses -1. These are the indexes of vector or array. You are given an array of prerequisites. The prerequisite of I is defined as this AI BI indicates that you must take the course BI first. If you want to take course A of I, means your B is dependent on A. If you take the course A, then you will be eligible to take the course B. For example, the pair this indicates. This is explained similar to the above one. You need to return the true if you can finish all the courses, otherwise return false. So in this question you have to find the DAG graph, and DAG graph we can use the topological sorting order, but here we don't need that. We need to return true when we can find the means we can take all the courses, then we return the true. When we will not be able to take all the courses, then we return the false here. And there are two examples, 2 courses and output true. There are total of 2 courses to take. To take one, you should have finished the course 0. Yes, so it is possible. Now we have this second example. Read this one, and there are the conditions given below. Number of courses can go maximum up to 2000, and prerequisites at vector array length can go up from 0 to can go maximum 5000, and prerequisite of I dot size. It means we are having the, I guess, pair of 2. And AI, BI can go up to from 0 to num courses. All the prerequisites are unique. So now I will go and go towards the explanation of problem which we have started. This is the function which is given to us to implement. We have to complete this function. Here and various vector is pass given to us as the input. This n is the number of vertices or nodes, and this is age. Age is vector. So what we will be doing is, inside this, we need the associated vector, and initially we mark all the nodes by the false value, and we make the recursive path. Same thing we done with this recursive path vector. All node false, and we run the nodes on the neighbor here. All the neighbor nodes from 0 to n, and d are equal to 0, I less than I plus plus. Inside this loop, we have checked the condition. If neighbor is not visited, we will call this function. It's cyclic DFS. We are checking the cycle condition using DFS recursion. Okay. We have made this function. Just before this function, we have called this function for the node I and marked that node I as visited and its recursive path. If it again comes, and it is obviously. So these are the 4 parameters of that function, this cyclic DFS that we made before this function. So if it means if this condition is true, since it is placed inside of, so there is cycle exist. Because this is a cycle, so we will return false here. And this, so by after the end of this for loop, if cycle not exist, we will return the true. After this, I will explain you the above function. Let me explain now. Let me explain you the function is cyclic DFS, which is written just before this function can finish. This is the custom function we use to check the cycle. Here in this function, we pass the source visited and path, recursive path. From some information from this function at the top function. Source visited and recursive path. And it is and initially mark the visited true, and in this also we marked it true. And here we are not running in this cyclic DFS function, we are not running our loop on the neighbor. The long reason is explained here. Just cut this line. The logic starts from here. That we don't know here कि source node के कौन से neighbor है, क्योंकि हमारे पास edges की information है वो scattered है, because यहाँ कोई भी node इधर से उधर dependent है, एक node से दूसरी node पे हुआ है, एक से दूसरे पे, तो we can check for all edges. We have to check for all the edges, 0 to edges dot size less than edges dot size. We have to run the loop at the all edges. Here inside this edges loop, we made the neighbor as v, which is edges of I comma I of 0, and u as edges of I of 1, which is source. And after determining the neighbor and source, from this condition we say we found the source node u equal source, then means we found our source. Now inside it we check the condition. If we have not visited the neighbor, then we will call this function is cyclic DFS. Similar recursive function inside this function for v. This is source here. V means earlier our source was u. Now if our neighbor was not visited, we visit the neighbor v, and this time our source will become v, and we mark it as visited and mark it on the recursive path and edges and return true. Because there is cycle, we return true. And this is the after this outer if we have written the else if, which is else case of this neighbor not visited. This condition is when neighbor is visited. Neighbor already visited hai, and we have the recursive path of v. Neighbor means I guess it is coming twice, so that's why there is this condition is of I guess baggage condition. So there is cyclic present, so that's why we return true. And at the end we delete the source node. This is the step of backtracking and deleting. We backtrack and delete the old nodes and return false when we don't have found cycle. Now after that course scheduling problem, I've also solved its second part. And problem statement is also similar, but we have need to do one different thing. We need to return the order of courses you should take to finish all the courses. Means we have to return the order of courses here. We need to return here the topological sort because of the directed graph. So in that directed graph, topological sorting is possible. So we need to return the order of courses. And if there are many valid answers, return any of them. Means any one of them. If it is impossible to finish all courses, then return an empty array. Means when cycle is present there, then we need to return the empty vector. It is simple. This is its example. The total of two courses to take course one. This is the example explained, and these are the constraints given to us. Prerequisite dot length. This is also a vector, I guess. Its length is num course. Num course is basically vertices or nodes. So n into n minus 1. It can prerequisite vector can go to maximum length n into n minus 1. And we have seen this. Are both nodes should be different and all the pair are distinct. Now I'll go on the explanation part. The main function that is given to us for implementation was this find order function. Here what we did initially was we made bool visited vector. So inside it we've passed the node n, and this is 2D vector edges. We passed it. This information is basically given in input. Now what we done is we made the visited array marked all falses. This thing you know, and after this we made our answer vector. This vector which we have to return. That's why we created this vector, and we will return it at the end. This is empty answer vector, which is courses vector that we return at the end. We make it of integer type because we have to return the number of courses. Now we run our for loop on all the nodes. Integer equal to 0, less than n, plus plus. If node, since we are run on I nodes, so if our neighbor is not visited, so it can be taken as I, not bool this time, because we are running taking I pointer. Inside this, if it is not visited, so we have called this function is cyclic DFS, and we have made this as I as our new source, which was not visited earlier, and marked it this source as visited and called for recursive path and edges. These parameters are necessary. These parameters have been passed because these parameters are necessary to code the logic inside this function. And if cycle is, since we have a cycle present, that's why we made this empty vector and there is cycle present. That's why we returned that empty vector. Now after the end of this for loop, we made the step and reassign all the values. False all the node value of this visited vector. We have Assign means reinitialize all the nodes value to false. This visited vector. Again, we are reinitializing visited vector to false. Because here we took the stack data structures. We have already implemented stack in some past problem. We again run the loop all on all the nodes, and if neighbor is not visited, then we call the topos logical order and mark it as visited. Mark that I node as visited and push the stack, call for stack and edges, and we run the while loop on our stack when until and unless it gets empty. So what we are doing here is that in the stack, from the top of that stack, we are just pushing our value to our answer vector, which was empty at that time. Okay, then we are copying the values from the top of the stack. We are pushing the value from stack to that empty answer vector, and we are just popping all the values from the stack. Means we are making stack empty and storing the topological sorting order in our answer vector. To make it, we store the topological order inside that vector. Earlier, that answer vector was empty, so we will return that answer vector, which has stored the topological order. Now I will explain you my custom function that we made. I wrote after that main function. This is the cyclic DFS function. We are using it from many times. In this function, we write the logic to detect cycle in directed graph. Inside this function, we pass our source and visited by reference and recursive path and 2D 2D vector or 2D array edges. This is generally empty 2D vectors, I guess. And this is obvious thing. And this part we did in its course. This loop we have run on all the edges on our course scheduling part 1 problem. And this is again also a similar logic. Okay, so I've explained this function. Now I will explain you this second function. This second function logic here is different in the course schedule part 2 problem. We need to return here the topological sorted. The logic of this function is topological sorting. We have passed the source related stack and the edges. This four parameters is necessary. We have passed this 4 parameter because these 4 parameters are needed to take out this topological sorting order. So initially we will mark all the source node in the visited array to be true and run the loop on the edges. And we did that similar logic. Now instead of calling this cyclic DFS, we call pickle order function. If here V is not visited, so we will mark the V here source and we mark this source as visited and we call it for stack and edges. So at the end of this for loop, after the end of this for loop, we pass the source onto the stack. Source means all the nodes in the stack, which was the order of topological sort. I guess. Just try to drive in. The time complexity here is big of V plus E. Nodes or nodes that is vertices. So vertices plus E. Edges. Node plus edges. That we are not called as is cyclic DFS because we are inside the topological order function. So we have called for it.
Says this problem is about binary search basically. So let's read the problem. Given a sorted array of distinct integers and a target value, return the index if the target is found. Means what we have to return? We have to return the target of index if it found, but if not, target is not found, so return the index of the target where it would be if it were inserted in order. This array is sorted, that's why there is written nums contain distinct values sorted in ascending order. Binary search application.
That's why we have to implement it in big of log and runtime complexity. Start and while loop. Start as a quit window. And I have modified formula of build. And first condition we compare is of when we found our target in the element matches with our target. Index with element match with target. Then return target as index. And for that sorted part, nums of started less than equal to nums of middle. Then inside this if another if will come, that is nums of target is lying between start to mid, that is left part. So our target, we search our target in between start and middle. So nums of target is less than equal to middle. Nums of start and then simultaneously our target should be less than equal to nums of mid. So we update our end index to end minus 1. Otherwise, for right part, this else case is for what? We go over start equal to mid plus 1. Start. We take our start to the mid plus 1 position. And after this else case, we reach to another else part. After completing next socket, this else part is of right socket. If my target is in between mid to end, means target is greater than equal to nums of mid, and simultaneously our target should be less than equal to nums of end. Then we do start equal to plus 1 or else and equal to mid minus 1. And at last return minus 1 when we not found our index.
This problem is about deconstructing the binary tree from the given preorder and inorder traversal. Here we have given the preorder and inorder traversal order, so we will construct the binary tree from that order. Here we have the another problem of the binary search tree, which is the recovered binary search tree. Here what the statement of this problem is, or what this problem says is, we have in our binary search tree we have given some wrong nodes. We have to swap the incorrect pair of nodes. We have to first find the pair of the incorrect nodes, and then after finding those nodes we have to interchange means we have to replace. Interchange means we have to swap both the nodes. And here are in the description, here are the examples on which we can dry run our problem. And there is some constraint: number of nodes and tree ranges and node values and follow-up. Means a solution using this much space is pretty straightforward. Could you devise a constant space solution? We have written the solution, which is having the time complexity of big of n because of inorder traversal, because we are traversing all the n nodes of our tree, and having the space complexity here is big of n. Why big of n? Is because in this function, this is base case and this is our recursive call of this function used. That's why it's recursive call stack, recursive call stack of n depth. We have the space complexity big of n. Space complexity here comes because of the call stack depth or recursive call, and this swap logic uses the variable. That's why its space complexity is constant. We cannot count its space complexity. Only this is the main function from our problem, and this is the function which we have passed. Inside it we have passed the root and made it above. We have passed the tree node star root. In the inorder we have passed our root, and this is our recursive solution. That's why our space complexity is big of n. And we have initialized the three variables: first, previous, first and second, all of them by null. This is base case. If our root is null, root means current node at which we are standing, and we are calling the inorder for our roots left. And this is condition check. Previous, if our previous is non-null and previous value greater than root's value, this is the condition to check whether we will. This condition is to find the wrong pairs that will be arranged in our tree. Then after fetching those pairs, we will swap that pairs to get the correct order. Also, if this first is null, then we will store the previous in our first and root value, and after if condition we will store the root in our second, and for update the previous for next iteration. Previous is equal to root, means we are storing the root in the previous. We have updated the previous for every next iteration, and we will call here the inorder for roots right. Simply, this is for inorder we are following left and root, then right. So this is left part, and this is for root part, and this is for right part. This inorder function is to do inorder traversal, and this recover by BST is the function to. In this function we are writing the swapping logic. We have only passed the function in this main function. We have passed this inorder function in this main function recover tree, inside which we passed the root that were passed on our inorder function before. that we made, and then we wrote a logic to swap the values. This is the method, simpler method that we have already studied earlier in our arrays topic, temp swap method, swapping two numbers. Well, in this step, that first of all we have to perform the inorder traversal. Then till here, this point, at the end of this inorder traversal function, after traversal, we will get the first and second value, I guess. Then after this function call, we will reverse the first and second value by this temp swap logic. That's it. A new problem called number of islands. We have given the m cross n binary grid in which there are entries of 0 and 1s. 0 represent water and 1 represent land. We have to return the number of islands. Means group of 1 से जो component बन रहे, we need to return that, the component formed from the group of 1s. You can read this description, and also there is some example given and constraint given to us. This m is the grid length, n is grid of I dot length. These two things we will come to know when we have studied the 2D array. We will come to know that number of rows and number of columns. There we have used the nested for loops. We write terms like this: m and n will range from, can maximum go up to 300, and grid I and G can be either 0 and 1. Now I will start explaining you the solution. Here, although initially we have given this function, this number of islands, in which there was grid passed, which character array, which is having 0 and 1's entry. Okay, here we have initialized the variable islands. We have to return the number of islands. That's why we made this variable called islands and initialized it with 0, and n we took it as this grid dot size, and m is grid of 0 dot size. In a constraint, from the constraint we are using this data, and okay, these are the variables that we have initialized for our grid and for this value that we have to return. And this is a 2D vector. We have created this 2D matrix. Initially we have initialized this m cross n grid with all false values. We have created it and initialized. Okay, then inside this island function we have run the nested for loop on every cells. We run a loop on every cells, nested loop. उसमें किसी भी सेल में पता चला कि if this I guess for row, our outer loop is for row and this is for I guess column. Now in this nested loop we are checking this condition. If we found once and it is not visited, then we will call DFS to mark that one as visited one component from each land which shares its area, and then we do island plus plus so that it can count its adjacent neighbors of ones. means islands, land part. And after ending this for loop and checking this condition inside, and after exiting this loop till at this point we have calculated all the number of the islands. Then after calculating we return that number of islands. The number of islands is equal to the number of total component of ones or of the lands, whatever you say. Lowest common ancestor of a BST. Already we have done the LCF problem in our binary tree data structure previously. Now the problem description is this one. You can read it if you want, and this is the examples and input output given to us, and these are the given constraints which is important to consider. The constraint are number of nodes in a tree is from range this to 2 to this. These are the minimum nodes required to make the tree, and then node value. All the node value are unique. Means because we are dealing with binary search tree, so our node value should not match. We will always see unique values of nodes, non-repeating number. This is similar meaning, and P and Q exist in a BST. Okay. Now we will move on to our explanation part, and this is the function that we have to complete, and its return type is node start type. Means we need to return the node at the end of our problem, and this is the function LCA, in which we have given the root and given the node P and Q. We have to tell on the basis of these two nodes that what will be our ancestor for this given node P and Q, and this is the base case, because we are here doing the recursion. That's why we have to deal with the base case. So if our root is equal to null, root is null, so we will return the null value. In that case we don't have LCA. When we return null, we will not get any LCA. Now first case, if root value greater than P value and simultaneously it is also greater than P value, then we will get our LCA from the left subtree part. So we will return pass instead of roots left, and P with P and Q. And it's else case. If root value is lesser than P value and its root value is less than Q value, then we will find the answer from the right side. That's why instead of roots we have passed the roots right with P and Q. P and Q value will not change because we are taking the P and Q value once if we are taking out the LCA for it. And in the else case, its else cases, root value is smaller than one of this P and Q value and greater than the rest one, the other one of P or Q value. In this case we will return the root as our answer. This is an algorithm called convert sorted arrays to binary search tree. It is marked problem 108 on LeetCode. Easy. What the task given to us is here this array is given where elements are assorted sorted ascending order, converted to a height balanced binary search tree. Okay, so if we are having a sorted array, means we have given the n-order traversal of binary search tree. That is always a sorted array like. Now we are having this examples and this constraint, means our length of array can go up to maximum this value, and its element at index will go up to maximum this. That this condition is given. Nums is strictly increasing order. Now we will move on to the solution part. Okay, so we have given this function sorted array to BST, where we have given this nums vector passed with this reference. Okay, so that changes will reflect. This is, we will return the root. So we have made, inside this sorted array function, we will return the root at the end. That function we have made here, helper. In first parameter passed as, we passed as our array and 0 starting index and ending index, which is the last index, size -1. Okay, now this is our main function inside which this function is called. That's why we have created this function above. Since we have this function called inside this function, that's why we have created this helper function just before this sorted array function, and we have made this function of same return type as that of this one and passed this nums array. This is common, and inside which we have passed the start and end. Now since this is a recursive function, so we wrote the base case initially. What our base case was, when our start is greater than end, means we will get the invalid range of array. Then we will return the null value. And now we will, since this is the question of binary search tree, binary search is coming. That's why we have to first calculate the mid. This is the formula that we have earlier studied in our binary search. Okay, so we have calculated the mid, and then we made the new root node of this return type, tree node star root equals to this new keyword dynamically created tree node inside which we passed the nums of mid. It means we are running the mid pointer index, mid pointer in this array we are running, and finding the mid by this formula. Okay, by putting this start and end. First we started the extreme left side and at the extreme most extreme right side. Then we have calculated this mid, and by this mid we have calculated the value of the nums at the mid index, which was our root. Then we will, after creating the root, and if you are not sure, I will tell you, root node is not always the topmost node. It will be the any current node at which we are standing at each iteration. Okay, so after building or creating the root node, we will call this function recursively for our root left. This function call is to create the left subtree part. We passed for left part. Our start is this and and is mid -1 for left part. Okay, and root right. This is the call to build or to create the right subtree. Okay, so right part is from mid +1 to end, and then at the end we have returned the root. Means we are forming the branch wise connection. At the end we will form the connection. Till this stage we were creating only nodes, and by this we are joining them via branches or edges. It is Inorder traversal. The problem of Inorder traversal. Now let's read the statement. We have given the root of the binary tree, which is always in the form of input given to us. Written the Inorder traversal of its nodes values. We have to return its Inorder traversal order. Suppose if this our sequence is this, then our output will be this. This is the Inorder sequence, and if this is input, this is output to this root. These are the example, and this is the constraint. Maximum of the nodes of a tree goes up to 100, and node values till 100. And here already we have done this problem by the recursive method, but now we have asked to solve this problem by using the iterative approach here. So here is our iterative solution by which we can solve this problem. Now we have to complete this function called Inorder traversal, whose type is vector of integer. Since this is our return type, that's why we have to return the answer in this format. That's why we have made the vector of integer, and we made the answer vector integer answer, and we will initialize the root. This is given to us tree star node by this type. We have made the current node and initialized to root. Now we are here following the steps of from here to here. We are following our normal Morris Inorder traversal. This is generalized approach. that we are following here. If our current is not null, means our current should be valid, then we will do current ka left. Then we will check for current ka left. We are checking if current ka left is null. Then we will push in the current value to our answer. We are pushing the current's value to our answer. Means in our Inorder Morris traversal. Now we are updating our current to its right. Doing this to traverse our tree, and opposite case of if else, what we are doing there is we have to find the Inorder procedure, means the node which are coming to the left of our current node. This is Inorder procedure, which is our current left. Okay, and we have run the while loop till this condition. If our right of Inorder procedure is not null and right is not current, then we will update the current Inorder procedure to its right. Similarly, that we have updated our current to its right, we are updating here this where our pointer goes. Okay, now we will check for more conditions. If Inorder is right, we are checking for if Inorder right is null. So Inorder right, we will make connection and we will update the current to its left, and in its else case we will destroy the connection. IP correct is equal to null. By doing that, we are destroying the connection and push current key value to the answer and updating our current to its right, and then returning the answer at the end. After the end, the new problem, which is lowest common ancestor of a binary tree. Yes, as you can see, this is a medium level marked question on lead code. Here we have given the two nodes P and Q. For these two nodes, we have to find the lowest common ancestor. Now, in general, you need to know that what is first of all LCA. Least common ancestor is either parent or its parent or higher order parents. All these are called as ancestors. We have to find common ancestors. Which will be found very close to both the nodes P and Q. That's our main agenda or focus of this problem. And this is given example, input and output. So you can understand all these examples from there. And also you can dry run also. And these are the constraints given to you. Both nodes P and Q should be different, and both should exist in the tree. and all values of nodes are unique. Node की value की range, and this is the value, node value. Maximum the node values go up to 10 to the power 9. Okay. Now let me move on to our solution. Here we need to complete this function given to us. Here what we have given in input, we have given the root and the nodes P and Q. Okay, this is of type tree node star, and our return type is tree node star. This similar thing we have seen in our build tree function, this return type. So here we will use the recursion. That's why we have written our base case first. We have to write the base case first while we are dealing with the recursion. So our base case will be, if our root will be null, so we will return the null in that case. Null as a ancestor. We will not pass any node value to its above node. Now if our root की value equals to p की value or root की value equals to p value, so we will return root in that case. And here for the tree we are calculating the left LCA. Now for calculating here we are not using any type int LCA. We are using the tree node star because our return type was tree node star. That's why for calculating the left side value we use the tree node star type. Now for left LCA calculation we will recursively call this function and pass. For left LCA we will pass root ka left, and for to find P and Q, for P and Q we have to find the left LCA. That's why in first parameter we have passed root ka left, and then P and Q in second and third parameter. Similarly, but we have found we have to find the right LCA. Again we call the function for root right, and P and Q we passed. Now we made this case left LCA and right LCA. This case we will understand better from the nodes itself. Although I am closing my explanatory part, which is called the diameter of a binary tree. A problem where we have to find the diameter of our given binary tree. Okay, so this is the problem statement. You can read, and at the bottom we are given the examples and the constraint below. Now let me, instead of wasting on time in this, although we have to look at the constraint, the number of nodes in this range and node values minus 100 to 100. Now instead of reading problem description and wasting time on it, I will directly go on the explanation of its solution. Now since we have to calculate the diameter of a binary tree, so our main function is this one, diameter of binary tree. We have to complete this function. we have given the root node of a tree. Okay, so from this given root we have to find the diameter of the tree. Now we have written the case. This is base case. Since we are doing here recursion, that's why this is the base case. If root is null, then I will return 0. What is this 0? This 0 is diameter. If our root node is null, in that case we will return 0 diameter. And although this step is also called as backtracking, we will return to its upper node the diameter of the lower node to the upper node. Now we are calculating the left diameter, calling the same function inside it and passing root left to calculate the left diameter. And similarly we will calculate the right diameter by calling this same function, recursive function, and calling for root right to calculate the right diameter. And we will then calculate current diameter. For that we will use the height function. Current diameter for any binary tree is the sum of the right height plus left height, or right subtree, height of right subtree plus height of left subtree. So we have added these both to height of root ka left, means for the left subtree and the right subtree we will add the height of both and add it to give the current diameter. Now to return the final diameter, we will return by taking the maximum of these two, left and right diameter. Then we will taking with the maximum with the current diameter. That will return our diameter. इन तीनों में से जो बड़ी वैल्यू होगी, that will become our answer. Now while calculating the diameter, we have used the height function also. That's why we have made the height function at the top. This height of a binary tree problem we did it earlier. Now what we did in that was basically we have given the root node, and for the base case we will return, if our root is null, we return 0 height from the null node to its top node while backtracking. And we will calculate the left height by calling the same function for the roots left, and right height calculating by calling the height function and passing the roots right. Now at the end we will return the max of left height and right height, and plus 1. This will be our height. Okay, but now here our time complexity of this problem, or this diameter function, is not big of n, but it is big of n square. Although the time complexity of this function was big of n because we are traversing n nodes, but inside it the second function is used whose time complexity is also big of n. That's why our total time complexity of this diameter function is big of n square. Later on we will optimize it for more better approach. We will optimize its time complexity from big of n square to big of n, from square to linear time. This is our new problem, gas station. From the topic Q, having n gas station means we are having the gas station, gas array, in which we are having n stations out there, n indexes. Corresponding to those n indexes, we are having the n values, where it is saying where the amount of gas at ith station is gas of I. Okay, and this is a condition. The condition given to us: you have to begin the journey with the empty tank at the one of the gas station. You have a car with an unlimited gas tank, and it cost of I of a gas to travel from I station to its next I plus 1 station. You begin the journey with empty tank. Empty tanks means zero. From zero, we have to start our journey. Our gas station, given two integer arrays, gas and cost. Return these two arrays are given to us, gas and cost. We need to return the starting gas station index. If you can travel around the circuit once, means we have to complete the circular path here in the clockwise direction. Otherwise, return -1. If there exists a solution, it is guaranteed to be a unique. It will be a unique solution, obviously. And these are the examples given to us, for which the test cases has been tested. And we are giving this constraints: n equal to gas length and cost length. The gas and cost arrays are same because we are having the same element in both, and length can go up to maximum value of 10 to the power 5. Gas of I and cost of I, its element maximum can take the value 10 to the power 4. Then put is generated such that the answer is unique. Okay, so now let's move on to the solution and explain you the whole. Since we are here given the function can complete circuit, we have to complete this function, and there is two vector arrays given, gas and cost, with this reference passed. These both, because we need to keep track of our change in values in the arrays. Now we are starting with the total gas and total cost. So initially we are starting from the zero fuel. That's why we took this total gas as 0, and total cost is also 0. And we run the two for each loop, and integer value that belongs to the gas means this gas array. For the first loop, we are doing integer value belongs to this gas, this one vector. We are every time calculating the, हर बार टोटल गैस यहाँ पे कैलकुलेट कर रहे हैं, मीन्स वी आर अपडेटिंग द टोटल गैस here in this loop every time by the total gas plus equals to value. And similarly inside the second, for each loop we are doing integer value belongs to the cost. This value belongs to this cost. Second vector, this value belongs to into val belongs to cost. Similarly, same thing we are doing here. These are the variables. Since initially at the top we are made this variable by writing it, that's why we are not using or writing with the int inside the for loop. We will use this variable by its name, and this is the this is the case when our total guess is less than. After the end of this 2 for each loop, we will check the condition total guess less than total cost. Means to reach to the next station, if our total guess at the current index is less than the required guess to move to the next station, then we cannot reach to the next station, and also we cannot complete the circular path if we can't reach to the next station. Then after this condition, these are the cases below are the cases of the unique solution always exist if greater than or equal to fuel, which is if this condition greater than or equal to fuel is means whatever be the fuel which is required to move to the go to the next station, we are having the equal to or greater than that fuel, then we can reach to the next station. And we also here made the start index and initialized it with 0, and current guess and initialized it with 0. These are the two different variables. Now we run the for loop. Now here, after initializing the start index and the current guess with 0, we run the loop on the guess array or vector, whatever you say. We run the loop on the guess array or guess vector, and every time we are calculating or updating here the current guess, the current station at which we are standing, we are updating it as current guess equals to current guess plus guess of I minus cost of I. We have updated it every time. And now after that, we've also checked the another condition, that by if we check the condition that if for any iteration if our current guess came out to be negative, we will update our start by I plus 1. This start I'm talking about. And also we will reset our or reinitialize our current guess variable with 0. Again we will reset it to 0. And finally, after the end of this for loop, or after the end last iteration of our loop, we will return our start index, which is the final answer of our question, this variable. And we can also make our code shorter by doing this some changes, like You are wondering why I did this step here in this for loop, why I updated this total gas by this gas of I, and also this variable by cost of I. Earlier I've used for each loop where I updated the both of this variable inside the individual for each loop. There I have used the value at the right hand side of this both variable updation, but why I updated here as gas of I and cost of I, because this gas of I and cost of I comes here because in first of for each loop I was updated the, this total gas variable where there I wrote the condition inside the for loop, and well belongs to gas. That gas comes from this gas vector, this vector array, and inside second for loop for each loop when I updated this variable earlier in second for each loop, I wrote inside that for each loop as int well belongs to cost. That cost came out from here, this cost vector array. So that's why I have placed in place of the value I placed both sides its individual arrays from which it belongs earlier in their corresponding for each loops. And HashMap. In this we have to design and implement the HashMap without using built-in hash table or inbuilt things. And here it says the three function given. First one is put, in which insert a key comma value pair, basically pair into our HashMap, and you can read this. Okay, so let we go with our brute force approach. This is our brute force approach. So for HashMap or HashSet kind of thing, we take 1D vector, and here I took its size, int size declared. Obviously its size is an integer value, it's an integer number, so I've took its size, and inside this function my HashMap I've initialized its size. At the top I declared, and inside this my HashMap function I've initialized the size with 10 to the power 6 plus 1, and from the array we know that if our size of an array is n, so its index goes from 0 to n minus 1. So here our index of the vector starts from the 0 and goes till 10 to the power 6. So this is our total size of vector is 10 to the power 6 plus 1. This 1 is because we are starting with index 0, so that's why it is going from 0 to 10 to the power 6. So that's why 10 to the power 6 plus 1 to 10 to the power 6 it's 10 to the power 6 plus adding the 0th index will, so we will include our size as 10 to the power 6 plus 1. Okay, so below it we use the vector dot resize function, and inside this resize we will pass its size which we made. Okay, so now for this HashMap function we will use the fill method. We will fill from beginning of the vector to the end of vector with the -1. This is we filled it initially with whole vector. We have filled initially with -1 value. That's our initialization of vector. Okay, so that later or at the end we perform this put, get or remove operation, we will change this -1 value inside this vector. We update this -1 value with +1, 0 or any kind of thing, whatever operation we are performing from this below. Okay, so here is our put function. Inside it we have passed the key and value. Here key is the index and the value. We have to put the value inside the key. Here key represents our index. So in vec of key we have placed value. By vec of key is equal to value. This is get function and we have passed the key. So this is get function. We have passed inside it key. We have passed key inside this get function and it returns the vector of key. What this vector of key will give us? It will give us value. If we pass key, so it will give us value. Means for any particular index we will get its corresponding value. So that's why we have, so this is return, this is get kind of function. In get we got the answer, that means we have to return the answer, so that is the value. Okay, so now below, so at the last, this is the remove function we have used. Basically here we don't return anything, so that's why its return type is void. We have not taken it to agent. Okay, so in remove I passed the key. So if I want to remove any key, any value, means this is vector of key which is value, so we will set it to be -1. Means if any value placed inside this vector, so it will be updated from -1 to any non-zero value, any integer kind of value. Okay, this integer kind of value. So if we remove, so again we have to reset that value by -1, so that our value of that vector at that particular index will become -1. That is the main catch here. So this is the brute force approach. This is not good. Its time complexity is big of 1 and the space complexity is not that good. See, the vector size 10 raised to power 6 plus 1. This is a kind of exponential space. We don't want this kind of large space. We want to reduce it to either big of 1 or big of n. So we'll move on to optimal approach. This was the problem which was given to me in the lead code. It is marked easy. In this I need to design and implement the hash set without using any inbuilt hash table library. And you are seeing all these conditions: add, contains, and remove. Let me scroll down and show you what are the given constraints of this problem. Our key are ranging from 0 to 10 to the power 6. We can have maximum key number 1 million, and maximum we can use 10 power 6 keys, and at most 10 power 4 calls will be made to add, remove, or contains. Okay, now here is our solution. To implement the hash set, we made 1D vector hash set. We made this by ourselves, and we used its resize function, vec.resize, vec vector, vec.resize, and this is that 10 to the power 6 plus 1. This is size, and initially we have marked all the value with false. Okay, so this is my set, my hash set class. This is add class key. Here what we are doing, we are adding the key to the vector. That means that value is present, so we made it as true. And in the remove function, we pass key to the vector, and if key removed, so that element will become the false. Again, we are doing with respect to this false. If we are adding the key, it means we are making this false value true of this 1D vector, on which every position, each and every block inside the value field is false, and this remove will make them false, even it is false earlier by this, or it became true by this. And after that we implemented this bool contains class. This gives the answer if this vector has that key or not present in it. So at the end, from this function, we have written this vector of key equal true. Here in Here in this version 1 of spiral matrix, we have not printed the matrix. Instead of printing, we have stored all the matrix in the answer vector. We made answer vector and push all these matrix in the answer by answer dot pushback. All these 4 cases, and at the end plus plus minus minus all these things, and this break condition. And at the end I return the answer vector instead of printing the matrix. Version 2 of searching to the matrix. Here in this question you will see all the rows are arranged in increasing order and all the columns are also arranged in increasing order. We can see that one thing in this problem is that the last element of, when we cross this last element of the first row, we will not guaranteed to get the bigger element from the first element of the next row. See, this all elements are smaller than this 15, and this 19 is also here, and this 3, which is smaller values, are starting here. So this is little bit trickier variation. And this solution is more simpler than the previous one. This is here given as input example. Whatever type of input or input example we take here, if code is correct and work perfectly for all type of matrices, whether it is of even order and odd order. If our logic is code is correct for all type of matrix, this is generalized code, and if this is correct for all kind or order of matrices, whether even or odd, then we run this code. All and every test case here will get accepted. Any test case or example we take here will get accepted, whether it will be of even order or odd order matrix case. And we do here it will accept it for every example and every cases, every given input examples, it will correctly run. Whether it will be these given examples, it will match with the desired output. And suppose if this another input we take, it will exactly match the desired output which is written here. So whatever generic code we write here, it must be correct. We should able to satisfy, we need to satisfy each and every cases condition sequence wise so that it works for each and every example, then it will run fine. So after running, it will match with our output will match with the expected output, which on submit will give me the correct expectation. So this written code will get accepted. So here our written code will get accepted for every possible input example matrix, whatever will be given cases input or example will be given here. It will run correctly for every examples. Every cases will get passed. New question, another question. Implement stack using queues. And this is our problem number 225 on LeetCode, marked easy. Here in this problem we want to implement the stacks using queues. So here we will take 2 queues and 1 stack, and our stack follows LIFO and queues follows FIFO. Okay, here we have to implement the myStack class, and these 4 functions we have to implement. Let me see if this is the example for understanding purpose. And there is some note. What it is saying, you must use only standard operation of a queue, which means push to, back, peek, pop, this kind of. Depending on your language, the queue may not be supported natively. And a queue using a list or DQ, as long as you can use only a. Okay, so leave this line. So our constraint is, our new element is from 1 to 9. We can push minimum 1 to 9 element. This is the constraint given to us. Maximum 9 new element we can take. At most 100 calls will be made to this 4 operation. Okay. So now I move on to the code explanation part. So here we took 2 queues, Q1 and Q2. Here we are using the stack using queue. So instead of taking 1 queue, we took 2 queues, Q1 and Q2. One thing to be noted is that the element at the top of stack will be same as the element at the front of this queue Q1. So we will do 3 steps to solve this problem. First one, we will push all the elements from the Q1 to Q2. Okay, then after pushing all the elements from the Q1 to Q2, our Q1 becomes empty. We will push the new element X, this X, which is 3. If we take the example of 1 to 3, we push the new element 3 into Q1. Then after that we will copy all the elements from the Q2 to Q1. Our elements are in order of Q2 as 1. So now, and after pushing the new element in q1 so our q1 is having element 3 and q2 is having 2 1. So after copying element from q2 to q1, our element of q1 becomes 3 to 1, which is the desired answer. And if we push 1 2 3 in stack, so our elements order in stack is like 1 is the most bottom, and then 2, and then 3. 3 is top of stack, which is the front of our q1. Then by doing this, our order of element inside q1 q is same as the order of the element placed in the stack. This top function is easy. Here we need to return the top of stack, which is front of q1, which is q1 dot front. Okay, so here bool empty. Here we need to return our stack is empty stack. So whenever stack is empty, our q1 is also empty, because here our q1 q is playing the role of our stack here, and q2 is our helper q. As we are taking the help from the q2, main function is push and pop. Let me walk you through the push function, implementing our push function. Inside this push, we have passed the element x, and now among this push and pop function, any one function from push and pop function, we can choose any function in which we can run the loop inside. So we have chosen the push function, and we run the loop inside it. So we have executed the pop function in constant time. We did the same step that we have mentioned in the notebook, that while जब तक our q1 node becomes empty, what we will do, we will push into q2 में हमने q1 के फ्रंट से एलिमेंट ले जाके पुश कर दिए q2 में, एंड देन q1 से पॉप कर दिए सारे एलिमेंट्स, एंड देन whenever q1 becomes empty, then we push the new element x inside that q1, which is 3 among the 1 to 3 elements. And now what we will do, we will apply the condition to q2. When our q2 is not empty, means elements are present inside the q2 queue, we will push the elements from the q2 front to q1, means q1 से वो q2 के सारे एलिमेंट हमने q1 में पुश कर दिए. q1 डॉट पुश q2 डॉट फ्रंट एंड q2 डॉट पॉप. q2 से सारे एलिमेंट पॉप कर दिए हमने. We have popped all the elements from the q2. Implement the pop function. What we did was, we have taken the answer, which is q1 dot front. q1 front, which is our top of stack, and we popped the element from q1 so that our element from the front of q1 gets popped, and we returned our answer, and these two last one are simple. That answer is q1.front, so that q1.front is our new element 3. That was our top of stack. No, I'm not fumbling here. Now, similar to our previous problem, implement stack using queues. Our next question is implement queue using stacks. This is implement the queue using stacks. So here we will take 2 stack and 1 queue. This thing we know, and here we need to implement the myQueue class, and these 4 functions we need to implement here. And these are the simple notes given below. We ignore these notes and these example. You can read this example for better understanding and clarity. And these are the constraints we have already read in the previous problem. Okay, so now we move on to the solution of our problem. Implement queue using stack. So here we need to stack S1 and S2. So in myQueue class, below this public, we took 2 stack S1 and S2. We implemented this push function with big O of n complexity. Big O of n complexity, we here use the loop inside it. We push the element. In this push function, we pass the element x. Simple. We are taking 1 queue and 2 stacks. So S1 plays the role of the queue here, similar to the previous problem, where corresponding to 1 stack, our queue plays the role of our stack. Similarly, here our stack S1 plays the role of the queue. Here in this while loop, we run till our S1 is not empty. We push the S1 element from the top of stack S1 to stack S2, and then we pop the S1. We are popping this element from the top of stack S1. Now push the new element X to the stack S1, and here when our stack S1 becomes empty from this while loop, by the end of this while loop, our stack S1 becomes empty. New elements remain, and here in this through this second while loop, we run this. All the elements of S1 came into stack S2. Now we will push the element of the stack S2 to S2 into S1. So we run our loop till our S2 is not empty. If our S2 is not empty, we will push the S2 element into S1. So S1 dot push S2 dot top. S1 में हमने पुश किया S1 dot push S2 dot top, and then we pop the S2 dot pop. We pop the element from the top of S2 stack, and now we will implement the pop function. Here this function also gets implemented in big O of 1 complexity. Big O of 1, which is constant time. Here we took the answer. Answer is our top of stack S1, which plays the role of queue. All the function we will use the stack S1. Okay, because it plays the role of queue, and pop from the S1, we return the answer top of stack 1 S1 S1 dot top and pop from the stack S1. Popping means we are popping from the top of stack S1 and return the answer, this answer that we fetched out, which is the top of our stack S1. Peak means top element. Corresponding to Q, the top element is our stack S1 dot top. We will return, for peak we will return the top element of stack S1, because S1 plays the role of Q. And for empty, since our Q is empty when our stack S1 is empty, so we return S1 stack S1 dot empty when our Q is empty. As of now, we implemented this, all the functions of the queue using these stacks. Thank you. In a multi-level doubly linked list problem, what we have to do, we have to flatten the linked list. First we have to traverse the linked list in a linear manner. If we found any node having its child, we need to go to that level also, and instead of including the next elements of the above level, we need to go to the one level down, next level below, and start traversing that level from where their child will occur. Then in that case, our child will become the new head of that linked list. We will exclude the top level from the whole linked list, and our problem will become that we need to flatten the rest of the linked list from next level to the bottom. So here, to traverse the linked list, we need to include those nodes in the answer. While we have traversed those nodes, we will include those nodes in our answer. And to traverse those nodes, to traverse the nodes of a linked list, we need to take our current pointer. Okay, if our current points to at some node which is having its own child, so we don't need to go to the forward direction after that node. We need to go and traverse from the next level, starting from its child node, current dot child. And since this is a doubly linked list, so we need to here found the both forward and backward connection. So we need to make sure one thing also, that our address should not lose from wherever we cut the connection. Since we have cutted the connection from the next of the current pointer, where at the top level where we leave the node traversing, we have gone to that node's child. So from the next level, if we start traversing its child from its child, we go linearly. If we do not found any child of any node in that next level, we will reach at the tail of that particular level. Then we know one thing, at every tail and last node has its next pointing to null. tails next or last node next always points to null. So we have to connect that next node as a forward connection by that node of the previous level, previous next, where we store the address of that next. From that part we don't want to lose the connection. So that was our forward connection. And for backward connection, what we need to do when we are traversing at the next level. So our first step should be current next equals to next. This is the step to make forward connection. This right side next is that next of that previous level in which we have stored that node connection, that we do not want to break that connection. So suppose this current reach at the tail of the next level, so its next will be null, but here to get avoid the next to be null, we have applied the valid next condition check. Next, if not next not equals to null, then we will point the current next instead of pointing to the null, it should point to the that next element, next node of that previous level where we were stored its address. For which we don't want to lose its address. And this second step is for making the backward connection. Means that next, that was in which we have stored the address before breaking the connection, its previous should point to this tail, to this current node basically, which was pointing at the tail. This is that node. So we are connecting that next previous to this same current node whose next was pointing to null. Okay, so let me discuss its code from the very beginning. Initially what we did was, first we have written our base case. If head is null, means we are having the empty list. So we return its head without doing anything. We return its head, and we made this current pointer and initialized it with head to traverse. Basically we here initialized current with our head. This is because we initially started traversing from the first node. That's why we initialized our current with head. Okay, so now we will use here while loop. This condition is current is not equal to null. We will move our current pointer till we don't get null. Means after last node, current will point at null. So we don't want that condition to happen. So that's why we made current is not equals to null. When we are traversing the doubly linked list, we came across the two cases. The first case is that we are having node is having its child exists. And the second case is node is not having the child of its. So when node is not having its child, we simply update the current. We move current by one step, current का next. Okay, so and the above one is the part. Above one is the part of what this if condition is current का child is not equals to null. Current means current का child non null है, means node's child exists here. So we will do here three things. What are those three things? What those three things are? We will flatten the child. We made here the next node in which we have stored the address, current's next address to this next node before breaking the connection after the current. Okay, then what we did, current next, current का next का previous will point to current. This step is to form the backward connection. My bad. So our earlier step is, before it was, we have flattened, we have called this flatten function here since our child was there, exist. So we called here flatten function recursively. We passed here current child. That will become our new head. Okay, that will become our new head of the next level, from which we are start traversing the flattened linked list next from the next level. This current का child will be our new head, from which we start traversing the next level, and we call this flatten function, and we pass this current dot child as head for each and every level. When we got the child of any node, we pass this as our head. Then later, this flatten function, what it will do, since this is a recursive function, so it will flatten the rest of the linked list, excluding the top level part, or excluding the above level part, and it attach its current dot next, where we have stored the next current dot next, where we that next node at the same side, at the same current dot next, it points. We attach it from there, current dot next, and this is our backward connection step. Current के next का previous will point to the current. So this is our backward connection step, and we will break the child connection current by making current का child null. So this connection from the previous above level to the next above level will break, but from this step current child will is equal current child will become null. This second while loop is for traversing the next level. When we were having the current dot child, current dot next node. So the second while loop is used for traversing the second level, next level, we can say, starting from the head of that next level to its tail. Since we are here using current dot next, so we want it to be valid. So current dot next is not equal to null. We stored that current dot next in that current before doing backtracking or making the backward or connecting with that next pointer of that current, whose address we have stored before breaking the connection at the above level. This if condition is, since here we are using the next, so we applied the condition check next is not non-null. Then we will do this two steps. I've already explained to you these two steps, and this is obvious. Then that current child does not exist, so we will move linearly. We update current by current dot next plus one step, and at the end, when we found the head of linked list, when our linked list will get flattened, we will point their head at the front of first node. We return that head. We returned its head. That start and while loop. Start less than equal to end, and our modified formula of mid. And first condition we compare is of when we found our target in the as mid element matches with our target. Index mid element match with target, then return target as index. And for left sorted part, nums of started less than equal to nums of mid. Then inside this if another if will come, that is nums of target is lying between start to mid, that is left part. So our target, we search our target in between start and mid. So nums target is less than equal to mid, nums of start and simultaneously our target should be less than equal to nums of mid. So we update our end index to end minus 1. Otherwise, for right part, this else case is for what we do our start equal to mid plus 1. Start. We take our start to the mid plus 1 position, and after this else case we reach to another else part. After completing left sorted, this else part is of right sorted. If my target is in between mid to end, means target is greater than equal to nums of mid, and simultaneously our target should be less than or equal to nums of n. Then wait to start equal to mid plus 1, or else end equal to mid minus 1, and at last return minus 1 when we not found our index. Search a 2D matrix. So you are given m cross an integer matrix. Here each row is sorted, means here we need to search, and there is sorted condition, means we have to think for binary search. Here the first integer of each row is greater than the last integer of the previous row, means it is increasing. We need to write solution in log of m cross n. As this is our input matrix, here is our target 3, so it is found in the input matrix, so our output is true. And this is in second example, this is our target 13, which is not found in this matrix. Okay, so we return our output as false. Here m is matrix dot length. Okay, and n is matrix I dot length. Length refers to here size of the matrix, and m comma n range from 1 to 100. This is our variation 1 of search in 2D matrix. Okay, so here we have given what search matrix function, in which here 2D vector is passed with their reference and target. Here we have to apply binary search on total rows. So we have fetched m here is what matrix size, and n is, till this is wrong, here this n is what, n is r matrix row dot size, like that, matrix each row size. Or we can say matrix 0th row size. So we have initialized these values here and here, so we are having start and end, and our condition of BS. If this is the case condition, then we will apply binary search, and if start will cross the end, then we will stop our binary search. And we have, after start and end, we have calculated what mid inside it. So here the condition is that if target, this is the case when we founded our target in the 2D matrix. This case is what target is in between this and this value lies. These two values are the values from starting of the row till the end of the row n minus 1. Okay, 0 to n minus 1. If both these conditions simultaneously satisfies, then we can say that a target is found for that in that particular row. So we return, as this condition is true, so we will do search in row. We will return like that. Oh, we'll search in row. We return this as a function. Here we pass 2D array and target and mid row. As you know, the next two cases, this is the case when we go right side. Our target is greater than matrix mid row. Then our start will become mid plus 1 and we will move right means downward. Here in this case of 2D array, we will move where? In case of 2D array, rightward here means the down. As we are printing the element of 2D matrix sequence wise from top to bottom, top to down, so that's why our down means right here, and left of 1D array means up of this 2D array, else case, which is we do end equal to mid minus 1. Okay, so our main agenda is to focus on this function. This is that function. Below is our main function and this is our function that for that in which we do our, this is a function inside which we perform search into the array. Here we pass the parameters like 2D vector, then target, then row. Okay. Here I have taken starting and similar to the binary search in 1D array. This all condition is almost similar to the binary search in 1D array. Here at last, if I'm not found, I return false. Okay. This is looking a little bit weird. But although this problem is pretty good and it's of medium level category, this problem here is find missing and repeating values. So A is our what repeating value and B is missing values in the grid. We made answer vector and unordered set. We here define A and B and take N as our grid size. EXP and actual sum and run both of these loops and storing the grid sum in the actual sum. Adding grid sum and actual sum, and here we applied the concept of unordered set. We are trying to find the value of grid of I, j inside if s dot find grid ij is not equal to s dot end. Then we mark as our a as grid of aij and push back a inside ans. This is our repeating value, and try to run with this break condition. You will come to know, or you will find that your case will stop at 9,7. And after that, this break we will inserted grid of ij inside the set. After this, we came out of the loop and finded the expected sum by the formula 1 to n square number. 1 to n sum is n into n plus 1 by 2 n. So 1 to n square range sum is n square into n square plus 1 by 2. So in whole sum R, B is the missing value, which is expected sum plus the duplicate minus actual sum, and we have pushed back to our answer B, and at the end we returned our answer.
Let's have a look on this stack. Here in this problem, we need to design a stack in which we have to do the 4 operations, inside which we have to do this 4 operations: push, pop, top. These are the 3 known operations to us. We have already studied this or executed this operation in the normal stack problem. But here came this function get minimum, which is new function. This is the extra new function which we need to implement in this problem. So, and we need to implement the solution with the big O of 1 complexity for each function. Means each and every operation of this function is to be executed in big O of 1 time complexity, constant time. Okay, so we will do this problem with 2 kind of approach. One approach is having big O of 2n time complexity, and we'll optimize it to big O of n later. Where big O of 2n solution. This is our big O of 2n solution. We have created the stack just before this min stack function. We do not have to write any or implement inside this min stack function to implement this function given below. These are the 4 functions given to us: push, pop, top, and get min. Okay. So we have created the stack here, stack of pair of integer and integer value, the first value, and tag as we have created. And when we talk about pair, we talk we also talk about first and second, pair dot first, and this is pair dot second. So our pair dot first is value and pair dot second is minimum value. And here we need to update the minimum value after each and every push and pop operation, and take care of this thing while pushing the one value into stack. Hash dot push, we push the value without any curly braces, but when we the pair of values, we push it with the curly braces separated by commas. Please do not make the mistake of pushing the two values inside this round bracket. Push it with Always push the pair of two values within the curly braces inside this round bracket. Every time we are pushing the pairs inside within the curly braces inside this push function. See, and for pushing the value inside the stack, we check the condition. Is our stack empty? And if our stack is empty, so initially pushing the starting value. At the starting, we are having both value and minimum value both. We are having same value, so we have pushed the value comma value, and its else cases that our stack is not empty. Our if case was when our stack was empty, but now our else case is that when our stack is not empty. Now we are having some elements inside our stack. So now in this case we have to track our minimum value. Now our minimum will change, obviously, because there are many values occurring. So that's why. So to take out the minimum value, we took the minimum of the value, which is this value which we have pushed before, and the stack s dot top dot second, which is this one, the second pair. This is minimum value. Minimum value represent stack dot top dot second. Stack के top का second pair. And once we found this pair of once we found we get the minimum value, we push inside the pair of value from a minimum value. This value, we push the value and this minimum value. And in the pop function, we simply need to do nothing. We need to just do only s.pop. And in the s.top, we only need to return stack.top first. And make sure in the pop function, stack.pop, our whole entry gets popped, means deleted. Our first value pair and second value pair, means value comma minimum value, whole entry gets removed. And here in this top function, we will return the stack.top.first. Our first value of the pair represent the top value. We don't take care the second pair. Our first value is the top value that we have written s.top.first. Perfect. Now inside get minimum function we have returned stack.top.second. Second is our minimum value. Okay. Our pair's first value is the value and our pair second value is the minimum value. So that's why we returned here s.top.second. Now we'll write the code for its optimal approach big of n. Hello friends, this is our problem valid parenthesis. Passed inside our is valid function by str from s to str. This is easy and to do step here. Now let me explain you all this whole code solution from the scratch. This is a question problem. No problem valid parenthesis need having three cases of parenthesis: opening round bracket, square bracket, and curly braces. And for these opening parentheses we need to match the same closing parenthesis corresponding to it. Then we can say that our given string is valid. And for valid string, there are these three conditions given to us, so that for which we can say our input string is valid. See this 3 points correctly. These are those three rules. And after these rules, there are these examples. And for these examples, output is given. See that this opening is round and this closes a square bracket. This is invalid, that's why our output is false. And this is true because for every opening parenthesis, we have the opposite closing parenthesis of it. This case, this is invalid because here this round bracket not match with square bracket, and this square bracket not match with this round bracket. So this is also false. And we are also given our constraint string.length. Maximum we can take our string length up to 10 to the power 4, and our string consists of parentheses only. This means it says character. In our string, this parenthesis must occur. Now let's move on to our solution explanation. Okay. So inside this function, after passing or given input string str, we have created the stack. Or you can say we have taken the stack. Initially this stack was empty, and then we have run the for loop on this given string. Okay, from 0 to, by using this pointer, right, from 0 to its whole length, string length, and incrementing this. And then what we did after it, we have to push the characters occurring in that string at some index I while we're traversing that string from 0 to its whole entire length. Okay, so that characters are here represented by a string of I. We are pushing inside the stack. st.push string of I means at every index of string we are getting the characters. So this str of I, this string of I, string str of I at every ith index value at every ith index of that string we get this character and we are pushing into a stack. We are doing this. Here is returning push character occurring at ith index of string. And after that we return false. Just leave this condition. When we push the characters inside the stack from the string, just after checking this condition, if we found any opening parenthesis, any one of these three, if we found any one from these three opening, then we push it into the stack from the string ith index. This thing's string ith index. Okay, and it's this initial cases, if cases found opening, and its else cases found closing. Means we found the closing parenthesis corresponding to this opening parenthesis, which is at the top of stack. Then we found closing bracket corresponding to the opening bracket of our top of stack in the string. Okay, then we will have popped from the top of stack. But here this is the condition. Stack top we are getting the opening parenthesis and simultaneously found its closing corresponding match at the ith index of a string, or this curly braces opening we found at the stack top of stack and simultaneously found closing curly braces at the ith index of string, or this third case might occur. At the top of stack we found the opening square bracket and at the ith index of string we found its closing pair, closing stop, closing square bracket. Then here in this case we will pop from the stack top opening pairs. We have applied here or condition. Why this is because if we got anyone closing from this three types of parentheses, if we got any one type of closing parenthesis corresponding to this three, corresponding to its three opening parentheses, then we pop its corresponding opening parenthesis from the top of stack. Okay, but before this condition we have checked that is our stack empty or not. If our stack empty, then we will return false here, because false means our string is invalid, not valid. So till this this else cases is of found closing. So after this else case, we check for if our stack is empty, so we return false. Means this if cases of, since we are using this checking this if condition after this inside the cells, which is of found closing. So this if states that closing quantity of closing parenthesis is more than opening parenthesis. Closing parenthesis is greater in quantities than opening parenthesis. So our string is obviously invalid. And here is the perfect case. If closing match with opening, if any one of this closing match with opening, simultaneously these two things occur simultaneously. And any one of these three takes place. That's why we applied OR here. Then we pop from the top of the stack. And this else case is of no matches, which is inside this else case found closing. This found closing wala. This else case is no matches. So this else case is opposite of this if case, where we got corresponding closing match of the opening parenthesis, where we popped the top element from the stack. But its else cases, we have not found any single match corresponding to the top of our stack. Our closing parenthesis does not match with the opening parenthesis, which was found at the top of stack. So here we return the false. False means again invalid string. And after the end of this is for loop. And after its end, we return this stack size 0, means empty stack. Empty stack means we have finished each and every. We cancelled popping. This is at the end. And last, we return our empty stack when we got our stack empty. After popping the top element, when we got corresponding closing character every time which matches with the opening character of the opening parenthesis. At the last, when we return this thing, stack empty, means we are not having any residual character. So it also means that our string is valid parenthesis. And its opposite case was that our stack size is not equal to 0, that our stack is not empty. Stack is not empty at the end. After doing all the operations, we remain with our stack left unempty. It means our given string is invalid because we have not popped each and every element of the stack top with the closing parenthesis that we found on the ith index of the string when it matched. But in this case, stack is not empty, means at the end our stack top does not match with any ith character of the string. That's why our stack top element not get cancelled. That's why we can say that our string is invalid. But here at the end, yet we need to return our answer, which is stack is empty. So this is final. Because at the last we have written our stack size equal 0. We are not directly saying that our stack is empty. We have used here double equal to. If this condition is true, this much I have shaded. If this condition is true, then it means we have all bracket opening brackets matched with the corresponding closing ones. This is the problem of this palindrome. Since we have to check in this problem, we have given a string, we have to check that this string is palindrome or not. So initially we will take the 2 pointers, start and end. We place 1 at 0 and at the last one is length -1. Then we run this while loop according to this pointer condition. And inside while loop we will check. We are checking to whatever be the pointer at the starting of the string. We are checking that is that the number at that location is character or alphanumeric or not. If it is not alphanumeric, not is alphanumeric of s dot start. No, f s of start. Then we will move forward. We will do st++ and we will continue. Means we continue the movement in the forward direction. We continually move the start pointer towards the forward, and the else if cases that our string of end, we check that our string of end, whatever be the number of our character at that position is alphanumeric or not. If it is not alphanumeric, then we will do and -. Continue. We do and -. Then at the last we will do what? We need to take care of the thing that we are comparing the two entities in their lower cases. We compare them in lower cases. We do not compare uppercase with the lowercase. So we have to convert both string of start and string of end. Whatever be the number or character at that position, we need to convert them into the lower position, lower case. And if that will not come out to be equal, if two lower of s of start is not equal to 2 lower of s dot end, then return false. We know that if this is not equal, then we can easily say that one is capital and the other is small. So we are getting almost unsymmetrical kind of string. So we can easily return for this case false. And we do st++ and -. Inside this while loop scope. And after outside the while loop, all cases over. And out of while loop, we will return at the last case our answer as true when our string is palindrome.
This is the only one case from which the string from the left side and right side is symmetrical. Then at the end, after getting out of while loop, we will return the true when our string is palindrome, like returning the answer at the last and end. This is the case whenever this case is applicable when string of start is not equal to string of end. At any single position, this string of start from left side and the string of the end at the right side. If any one position or any one case, any single case, if these two things are not matching any single time, then we report the return false. We can easily say that this string is not palindrome. एक ही पोजीशन के लिए काफ़ी है ये कहना है. किसी भी एक पोजीशन पर अगर स्ट्रिंग के स्टार्ट इंडेक्स और स्ट्रिंग ऑफ एंड इंडेक्स पे जो वैल्यू पड़ी है वो दोनों अगर इक्वल नहीं तो देन वी रिटर्न फॉल्स. That means our string is not palindrome. And after the if, in the scope of this while loop, we do st++ and end minus minus. This is the normal case that we are doing for scanning. One pointer we move forward and the another next pointer we move in the backward direction to checking. And one more function is left. Since when I made this function for comparison first time inside of the condition, so this is a main function which was initially given in the problem, and this is the function that we made to check. We made bool is alphanumeric and we passed the character char ch, and to check the condition of what if it is alphanumeric or not. So to check alphanumeric or not, to check alphanumeric, the condition is our ch char is in the range of 0 to 9, means char is greater than equal to 0 and less than equal to 9, means 0 to 9, or condition, or we convert our char to lower char. If it comes out greater than equal to small a, since we are converting to lowercase, then its result should be in between small a to small g. So that's why if we convert our character to lower ch, if to lower ch is greater than equal to small a, and to lower character is less than equal to small g. If it comes out from the range of small a to small b, including both, then we return the true value. Means this is, we are checking for alphanumeric. Then if this condition satisfied, then we can return true that our character is alphanumeric character, or else we return false that our character is not alphanumeric character. So that's all for this question.
You have to design a data structure. You need to implement here anything, we have to design here the least recently used cache. this class we need to implement here. We have to implement. And also we are given this LRU cache function in which capacity is given. Capacity is also called the limit of the cache. Get function in which we pass a key and we will get the output value. We pass the key in this get function and you get the value corresponding to this key. If we if this key do not exist, then we return S1 here. And this is put function. Put or push, whatever you call it. We will push by this function, we will push both key value here. Update the value of the key if the key exists. Otherwise, add key value here to the cache. Number of keys. The value of key exceeds the capacity from this operation. Evict the LRU key to implement. They're also given to implement the get and put. All this function in a big O of one time. And these are the examples as you are seeing. And these are the constraints given to us. The capacity going maximum to capacity or limit will take maximum value of 3000 and the key will take maximum 10 to the power 4 value and the value will take 10 to the power 5 at most 2 into this much calls will be made by this two function get and put. So initially for this LRU cache we need three things to implement. We need the doubly linked list and the map, usually unordered map. So here after the LRU cache class, we made this public and inside this public we made the new class just after this public. We made this new class and in the public we are inserted some data. The data is our key and value and the previous and the next nodes pointer. Node star pointer, previous and next. And we have written the node constructor for this class node. And we have passed the key and value inside it. Key and v as our input and this key and value from this data. We have stored this key and v which we have inputted into this node constructor. And we will initialize our previous and next with the null. And after the end of this class, I think this class, node class, we made the dummy head and dummy tail. Since we have made this dynamically, so we have used their new word and initialized the key and value both -1 for both of them head and tail node. And we made the unordered map of integer, and this integer is key and the second pair is node star. This is integer limit. And we make the limit variable which we will store inside the capacity of the LRU cache. don't focus. We will win here. Void add node function. Here we pass the node star new node test code. This these are the steps to add the new node. We have created the old next and initialized it heads next. And then we have written this 4 lines to add the new node. And then we have written the function to delete the node. And this is obvious. We have written this add node function. What it will do? It will add the new node to the doubly linked list. Okay, so that's why we have passed the new node. This new node will be added by this add function, add node function. Add node will add the new node, and there is no loop in this case. So this add node function is implemented in constant time big O of n. Similarly, this function is also here to delete the node. This is obvious. We have passed the old node. We will delete the old node. That's why we have passed here old node. Old node delete, and we will make the we will insert the new node. That's why we have written the add node, and we passed their new node. And we've written the 4 nodes, so 4 steps to delete the old node from the doubly linked list. And this is our simple LRU cache function given to us. Inside this, in this limit, the variable that we made just at the top, the limit variable. In that variable, we store our capacity that we passed here in the LRU cache function. We have passed as parameter the capacity that we are storing into that limit variable that we made above at the top. Let me erase this capacity. We are storing this capacity into that limit, that variable we made at the top just before this add node function, and just after this before add node, and just after this unordered map. Okay, now discuss the and this is obvious. Heads next tail. This is the initial condition when we when we were having the 2 nodes -1 and -1 -1. This is head and this is tail. There was no other new node. No node. We are forming the head and tail. We are connecting the head node with the tail node. So heads next will be tail and tails previous will be head. Simply, this is the initial condition, and this is a get function in which we pass key and we get the value corresponding to it. This is our base case. If we don't find key, m dot find, we have applied the find method. We have applied the check here. If we do not find, m dot find of key is equal m dot n, means we have not found any key into this map, so we return -1. Note star. And these steps are written inside in the notes. Okay, these are the similar steps. And at the end, we return our answer. When we get value corresponding to key, then at the end we return our answer. This is put function. Look its code. This is also implemented in BibOfN. Okay.
Problem are of our queue, which is the first unique character in a string. This problem is also called the non-repeating characters in a string, and this is our 387 problem on LeetCode, which is easy. Okay, what we have to do in this question, we have given a string s. Find the first non-repeating character and return its index. We have to return the unique characters index in the string. If it does not exist, then return -1. Means if any character is occurring more than one time. This is the case when all the characters of the string are occurring more than one. Then we will return -1. Then at the okay. Now this is all the examples explained you. Refer it, and here are all these constraints. String length can maximum go up to 10 to the power 5, and a string consists of only lowercase English letters. Okay, so here this is the function inside which string s is given in the input. Okay, so one data structure is given in advance to us. Okay, so we don't need to create the string here, like writing like string s. We have given a string here, so we can use it everywhere in the code, as you are seeing ss and s, like this. Okay, so now we will start the explanation part. Here we took the two data structure. One is unordered map and the second is queue. This unordered map is character and integer. Means here we will keep track of the characters occurring in the string, and this integer stores the frequency of that character. And how our algorithm works is, let me explain you how the algorithm of this problem works. Our algorithm is like, first we are having the map empty, so we will iterate the string by the pointer I from the starting index itself, from 0 to string.size. Okay, so while we are at first index, so our unordered map was empty at that time. So what we will do in that case, our map is empty, so and queue is also empty initially, because we are not having any characters. Okay, so if our map is empty, so we will push our first character, store its frequency in the map as 1 initially, but here we will start from the queue. Okay, so in the second iteration we will also do this same step. We will check inside the map if that character exists or not. Whether if it exists, so what is its frequency value. For the first column of map, we are storing the characters, and in the second column of value, first column is key and second column is value. First column we are storing the character, and in the second character we are storing its index. So if not index but frequency. In the second column we are storing the frequency of the character occurring in the string. Okay. So in the second iteration we also have to go to the map and check for that second character occurring or not. If occurring, then we can update its frequency from 1 to 2. If it is again occurring, to 2 to 3 we will update its frequency. But if it is not occurring, we will store that particular character in the first column of that map, and in the second character we will mark its frequency as 1, and then the character with the frequency 1, we will push that character into our queue. So from the first iteration itself we will store our first character and its frequency 1, and we will push that character into our queue at the front of our queue. So this process we have to do repetitively. So I run the loop on the entire string from the index 0 to its size, and we are pushing the index of the characters of the string into queue. But before doing this step, we are finding that character from that particular ith index of our string. From our string, we are finding this character at ith index in our string. This s of I is our character. At ith index of our string, we are find this character on the map. If this is equal to map dot end, this statement means that character is not found in the map. So this is the case of when our character is unique. It means it is having the frequency of 1. So we are pushing that character's index from that string into queue, pushing the index of that character from string to queue dot push. We are pushing inside the queue, and then what we are doing here after that here is this is its else case. So after pushing the index of that character to queue, we will also have to do this thing. We will check from a string we will check that character from string to the map into map if that character frequency inside our map is greater than 1. We will increase its frequency. This statement means that if we found any character at ith index of string, we check that character inside the map. If we found its frequency, because it is m of, it denotes to the second column, which is frequency. If we found its frequency greater than 1, so that's why we are doing here plus plus. We are updating its frequency. And this is when after the end of loop, when we traversed and crossed our last index of the string, then we will check inside queue. Is our size of queue greater than 0? Means is there element present or not? If there is element present, and simultaneously we will check for this condition also. This big condition is that we are checking the front element of queue inside the string. Means this is the front element of the queue. We are doing its s of. S of means we are getting its index from the string of that character which is appearing at the front of our queue, and we are doing its m of. M of this thing means we are checking the frequency of this character. S of q dot front, character which is at the front of queue. Inside string we are checking its index. For this character we are checking, this is m of. This thing is inside m of, means we are checking the frequency of this character inside the map if it is greater than 1. So we are popping from that character's index from the queue. We are popping means we are popping from the queue dot front. Always remember that we are always popping from the front of the queue, because front is the important element of the queue. Similar to as we are always popping from the top of stack. Top is important element in stack. We always pop from the top of stack. Likewise, similarly, here in the case of queue, we will pop the element from the front of the queue. There s dot top stack dot pop means here similar to queue dot pop here. Okay, so I made one mistake. Till this point our for loop does not end here. Our for loop ends here. After ending this while loop, our for loop ends here. That curly braces, I closed curly braces I have applied by mistake. Okay, so after traversing the whole for loop, or we can say whole string, after traversing the whole string by the for loop, we will return our two case. Our answer is of two case. First is when our queue is empty. Our queue is empty at the end when we will get all the characters with the frequency greater than 1. Then all element will be popped from the queue, so that our queue becomes empty. So we will return -1 in that case. Else, if we are having at least one element remains which is unique, so in that case our front becomes answer. So we will return q.front in that case. So let me also explain you one thing, the working of all the loops and conditions here. This for loop is used here to iterate the string, and till we iterating the string we are doing inside. Till iterating the string we are doing the what things we are doing. We are pushing the index of the character into queue and then increasing its frequency into the map, and then if its frequency is greater than 1, we are popping from the queue, and then at the last we are returning the answer after exiting the for loop. After exiting the for loop, or let's say after exiting the for loop, or we can also say that after traversing the whole string, when we crossed its last index, then we will check our queue whether it is empty or not. If it is empty, we will return -1, or if it's not empty, so unique element must be there, so we will return q.front as its answer, as our answer.
Variation 1 of next greater element. Next greater element, we run the backward loop. If this was the problem of previous smaller element, then we should run the backward loop for next previous smaller element. How this is different from the next greater element 2. And next greater element, we were taking the nums of s dot top. Here we are only taking string dot top index, not the value. This compare it with the next greater element 2 logic. Then we'll come to know better how next greater element 2 code differs by the logic of next greater element 1's logic.
Next greater element 2, the extended version problem of the next greater element. The description of problem, and here you see the examples, and below the examples there is output and the constraint given, and here on the right side I wrote its code solution. So initially, while storing here or running the loop, so I made n as a nums dot size. So wherever there is nums dot size, and there everywhere. Okay, so it's also better to do this step, because it is easier to analyze our time complexity of our problem with respect to n. That's why we made this nums.size as n initially, and we took a vector, integer vector answer it with n comma 0. You can also initialize it with n comma minus 1. See, one thing you must note, that whenever we will do addition in the array, we have to initialize our array or vector with n comma 0. But whenever we multiply the we initialize our array or vector with n comma 1, because we have to take the product with the 1. And in the addition we will initialize our array or vector with n comma 0, because we are adding those element to 0, adding the element with the 0. Okay, so that we will always add the element with the 0 to get that same element. Okay, but here we will traversing the answer array twice, so that's why we have to update the element at the indexes of the answer array. Update or replace, whatever you can say. So whenever we have to store or update or change the value of the element inside the array at their indexes, you have to make sure you have to initialize the array with its size n comma 0, or either with minus 1. This is different from the initialization while doing addition of the arrays. Here we are updating or replacing the values, so you can either initialize with n comma 0 or with an array size n comma minus 1. Both are fine. That will not give us error. Okay, so after this vector I took integer stack, and then I run my loop in the backward fashion from 2n minus 1 size minus 1 to the 0 index, and updating in backward fashion I minus updating I. And inside this for loop I need to remove invalid unnecessary elements, which are a smaller element, because I need here greater elements. So my condition, so I will pop those elements which are smaller. So this step we will do. Just before doing this step, we will apply the condition check. Stack size is greater than 0, means our stack is having some elements and simultaneously some value is present at the top of our stack which is less than or equal to the current element. Here I have not took current element as nums of I. I took nums of I modulo n, because wherever I need to the index, this is our output index to which output index of the is of size less than the Latin array. So that's why I took the output index. Instead of I, my output index is I modulo n. Whatever be the number of times I push the element from the array to that stack, I will use this value, and then this is my condition of smaller element. Then I will pop my smaller element found at the top of stack. I popped that smaller element from that stack. Okay, so after coming out of the while loop, my condition of smaller element will get finished, and after exiting the while loop, I will got the condition of the next greater element, which is this one. Push to the that I will store it to the answer first, then I will push its index, its current value index to the stack. We are storing the value into the answer arrays of, we are storing the next greater element values inside this answer array at this particular index I modulo n. Our condition is that doing this thing, if our stack is empty, store is store -1, and if it is not empty, then this condition, this nums of s.top, this is different from this. This was the condition of a smaller element, so this was the condition of greater element. So now here we found our greater element, so we store that greater element into this answer array. Okay, then we push the index push its index into the stack, and finally at the end we return our answer, which is our next greater element. That's all.